Welcome to this video lecture on the extended Bernoulli equation. It's also known as the energy equation. What we're going to talk about today is really mostly the derivation of this extended Bernoulli equation. It's kind of like Bernoulli's equation, but we can use it for viscous flows. Remember that Bernoulli's equation, as we've dealt with it all throughout the course so far, one of the restrictions of it is that we're dealing with inviscid flows. But if we're dealing with a pipe flow, as we discussed in the introductory video on pipe flows, if we're dealing with fully developed pipe flows, the whole flow field is viscous. So we can't use Bernoulli's equation to see how pressure is related to velocity. Instead, what we're going to do is we're going to go back to the energy equation, or the first law of thermodynamics, and rederive that equation and take into account viscous effects. And that's what we call the extended Bernoulli equation. So go ahead and take a look at your screen here. Picture I have here is of the Dogfish Head Craft Brewery. So it's a brewery. So some beer obviously is flowing through these pipes here, but you can see even in kind of a smaller scale facility, you still have a lot of pipe flows going on in that kind of thing. So it doesn't have to be a big chemical plant or gas refinery or something like that. Even smaller scale facilities like a brewery and such still have to deal with pipe flows. And so we need, again, to be able to understand how to analyze those flows. And one of the key tools for analyzing pipe flows is the extended Bernoulli equation. It'll be fundamental to all of our analyses of pipe flows. So a lot of what I'm going to do here is just a derivation. And it's not important that you know the details of this derivation. I only put it here just so you have it in case you're ever interested. The only real thing that you need to know about is how to use the extended Bernoulli equation, which we'll get to at the very end. So I'm going to kind of quickly step you through how this derivation works. But then, what you really need to know is at the very end of the lecture here. So what we do is we actually start with the first law of thermodynamics for a system. If you remember back to your thermo days, we have here on the left-hand side, the time rate of change of total energy of a system is equal to the rate at which we put heat into that, or transfer energy into that system via heat transfer, plus the rate at which we do work on that system. Okay, so you might remember that from your thermo days. I'm using the capital DDT notation here just to indicate that we're following a system. The total energy of the system is, we're writing in a kind of a general sense, it's the specific total energy times a little bit of mass. So remember that the picture that we typically work with here is, here's a system. So that's the volume of my system. Here's a little piece of fluid. It has some mass of rho dV. And so we take that little bit of mass, we multiply it by its specific total energy. That gives me the total energy for that little cube, and then I add it up over the whole volume of the system to give me the total energy of the system. The total energy, the specific total energy, is comprised of internal energy, or specific internal energy, plus specific kinetic energy, and specific potential energy. So the Z and G are in opposite directions. So if you increase Z, you increase your potential energy. Right? So we have internal energy that's related to the thermal characteristics of the material, like the temperature, macroscopic kinetic energy, and potential energy. So we start with the first law for a system. I'm going to go ahead and substitute in for my total energy there in terms of the integral, and then I'll use the Reynolds transport theorem, so you have to remember that from earlier in the course, to convert this into a control volume perspective. So here it's in a system perspective, now we're converting it into control volume perspective. So here's the time rate of change of total energy in the control volume. This is the flow rate of total energy out of my control volume through the control surface. So here's the mass flow rate, and those little bits of mass take some total energy with them as they leave or enter. Here's the rate of heat transfer into the control volume. Here's the rate at which we're doing work on the control volume. So we get this expression from the Reynolds transport theorem. The next step is we just rewrite the specific total energy in terms of our internal energy, kinetic energy, and potential energy. The next step is to rewrite this rate of work term, or the power term. I'm going to break it up into the power due to pressure forces and all other effects, so like pumps and things like that. So I'm going to just separate out the pressure in the fluid into a separate term. And I'll solve for that rate of pressure work based on, I'll just break it down into the pressure force acting on a small area. So that's what this is. So that the total pressure power acting on the control volume will be the pressure acting on a small area of the control surface. This is the pressure force. It's a little bit of pressure force. Remember, it's a negative because the pressure force acts inward on the area. And then I'm dot producting that with the velocity of the fluid as it comes in. So that we know just from basic physics that work is like a displacement, force dot product over displacement. So power, or the rate of work, would be the force dot product over the velocity, or dot product with the velocity, I should say. So this is just the pressure force dot product with the fluid velocity as it enters or leaves the control volume. And then we add that up over the whole control surface. And I can just rearrange that to make it look like this. I just wanted to multiply by a density and divide by a density because I want this term to look like this term. So then the next step is to substitute in this rate of pressure work term into my first law equation and then bring this pressure term over to the left-hand side. So now you can see the rate of pressure work has been incorporated into this control surface integral. And then over here we have the rate of other work. So this would be due to like electrical effects, rotating shafts, spring work, things like that. Then what we're going to do is we're going to assume that we're dealing with a steady flow. So that's one big assumption. Our extended Bernoulli equation will only be for steady flows. One inlet and one outlet, and that will be valid if we're dealing specifically with a stream tube. So if you remember when we talked about flow visualization, we have these streamlines. If I take some streamlines that are closely spaced together and form kind of a tube out of it, then that's called a stream tube. So whatever flow comes in here has to be the same flow that goes out there, right? Just because there's no flow across the streamline. So what I'm saying here is that we have one inlet and one outlet. So that's valid for a stream tube. You can kind of think of it as flow along a streamline. It has one inlet and one outlet for the streamline. So if we do make that assumption, then our time derivative term goes away, and then our control surface integral just deals with an outlet and an inlet. And of course, the mass flow rate at the inlet and outlet will be identical from conservation of mass. So the mass flow rates at the inlet and outlet are the same. The next step that we'll make is that we'll assume that the properties at the inlet and outlet, and what I mean by that are like the density, internal energy, pressure, those are all constant. The velocity I'm going to treat differently, but the pressure at the inlet, density at the inlet, same thing at the outlets, they're uniform. So I don't have to worry about integrating those over the inlets and outlets. As far as the velocity, that one I do have to worry about because we know from like the Navier-Stokes equation solutions, the velocity profile in a pipe is not uniform. It actually has a profile to it, right? So a real velocity profile, let's say it's laminar, looks like that, right? So it actually has a profile. There's the no-slip boundary condition at the walls, and it's maximum at the center. So when I have my integral over the control surface of the kinetic energy, I have to actually integrate that over the whole profile in order to get an accurate measure of the kinetic energy at the inlets and outlets. It's tedious. We don't typically want to do that. So it's just much easier to use an average profile, like what I'm drawing here. It's a lot easier to use the average velocity in the pipe rather than the real velocity, which is a function of radius in the pipe. Right? So it's a lot easier to use the average velocity profile. The problem is the kinetic energy here is different than the kinetic energy over here. Right? If I integrated 1/2 v squared over the surface, or the cross-sectional area of the pipe here, it would give me a different kinetic energy than using this one. So since I'm writing out the first law and it deals with kinetic energy, I need to get the kinetic energies correct. So what we'll define is what we call a kinetic energy correction factor. It's just a correction factor to make sure I have the same kinetic energies in these profiles. That way I can use the average profile. So the way we define it is we just take the kinetic energy using the average profile multiplied by the mass flow rate, because remember this velocity here is multiplied by the mass flow rate. So I'm going to take the average velocity, find the kinetic energy of that, multiply it by the mass flow rate, multiply by some correction factor, such that I get the same kinetic energy flux as the real profile. So this velocity is a function of the radius, remember. It's this profile here. So if I put in the real profile here, multiply it by the mass flow rate, and then integrate over that surface, I'll get a certain amount of kinetic energy flux. And I just want that kinetic energy flux to equal the same value over here where I'm using the average profile. So we call this value for alpha the kinetic energy correction factor. So I could just rearrange it like this. This would be like the real profile divided by what we have using the average profile. And what I can do is I can actually substitute in the velocity profile for like a laminar flow. We know what that velocity profile looks like, right? From our Navier-Stokes Poiseuille flow solution, we have what that profile looks like. It looks like a parabola. So I can plug that in here and calculate it all out. And when you do that, what ends up happening is you'll get the kinetic energy correction factor for a laminar flow is equal to 2. So I can rewrite this equation in terms of this kind of expression. And then if I'm dealing with a laminar pipe flow, to make sure I have the right kinetic energy, I just need to make alpha equal to 2. If you're dealing with a turbulent velocity profile, we don't have a solution for that. But a turbulent profile will have a more blunt-shaped profile to it. Let me kind of sketch that out for you. We know from boundary layer analysis of turbulent boundary layers, the turbulent velocity profile is more blunt-shaped. It's more average because of all the mixing that's occurred in the fluid. It's approaching more and more an average-looking profile. You still have the no-slip boundary conditions at the walls, but most of the flow looks kind of like the average profile. It's very blunt-shaped. Again, this kind of goes back to our boundary layer discussion, but it's happening because of all this mixing. If you look at this profile, it looks pretty close to the average already. It certainly looks closer to the average than a laminar profile, which is a parabola. So the amount of correction that we have to do for the kinetic energy is actually less and less. And so what we do for turbulent profiles is we're going to assume that it's about equal to 1. That we really don't need to do a correction because the actual profile, which is turbulent, and the average look very similar to one another. So there's very little correction we have to make for the kinetic energy. And in fact, as the Reynolds number increases and the flow is more and more turbulent, this approximation gets better and better. So for our purposes, we'll just say that when we're dealing with a laminar boundary layer, a laminar pipe flow, we need a correction factor of 2. When it's turbulent, the correction factor is just equal to 1. And again, the whole idea here is what we want to do is we don't want to have to integrate the real profile every time. So we're going to just use this in its place, but make sure that we correct for the kinetic energy so that we're accounting for kinetic energy correctly. Okay, so if we go ahead and assume these uniform properties for the internal energy and pressure and density and the potential energy, and then we make our correction for the kinetic energy, we'll get this expression. And I've rearranged a few things here. I brought the internal energies to the right-hand side. I put the outlet on the left-hand side and the inlet on the right-hand side. So I divided through by the mass flow rate. So from up here to down here was just some rearranging. Excuse me. Well, this grouping of terms, we group all in one place here. This is what we call a head loss term. And the idea is this. This term takes into account the conversion of macroscopic kinetic energy into microscopic or thermal kinetic energy. So because of these viscous effects, you can imagine that, as we shear the material and we have viscosity, that some of that work we put into it, some of that macroscopic kinetic energy or macroscopic work that we put into it goes into increasing the internal energy of the fluid, increasing the U here. So you get some increase in the internal energy when it goes out. It's going to be, the internal energy is larger going out than it is coming in. So this term will be positive in general. And then some of that may be lost to some of that heat gets lost to the surroundings and such too. There's a kind of a thermal effect here as well, heat transfer effect. But that's a loss of useful work, right? When we turn it into thermal energy, then it's going into microscopic energy rather than macroscopic energy. So we call this a head loss term. It's just energy being lost to heating, okay, kind of like frictional effects or viscous effects. So that's what this term is right here. This term is this one. So we call that a head loss. This other term, I'll highlight it in green, is what we call a shaft head term. So this other work, the only other work that we ever really deal with for pipe flows is shaft work. Shaft work is just caused by a rotating shaft, which you might have for a pump or a turbine or a compressor or a fan, something like that. And so we'll call that, this will be our shaft work term, and then this is called shaft head. So if we put energy in, or via work, like shaft work, then this term will be positive. If we extract energy via like a turbine, for example, then this HS term would be negative, okay, because this is the work being done on the control volume. So if you have a turbine, you're taking work out of the control volume. So that's called the shaft head term. So this expression is the extended Bernoulli equation or energy equation that the Fox and McDonald textbook uses. Okay, every term in here has dimensions of, let's see, it'll be energy per unit mass. Okay, so that's what this expression is. It looks pretty close to Bernoulli's equation, right? Except you have some extra terms. You've got this alpha in here, an average velocity, and this HL and HS term. So this is the form that your textbook uses, but most people in practice use the form that I boxed in down here. It's basically the same equation, but just divide through by the gravity. So you'll see instead of P over rho, it's now P over rho G. The Z term, just the GZ just becomes a Z. We'll go from a little h to a capital H. Those are just related over here. It's just capital H is just little h over G. So this is the form that I'll use and what most people end up using. Each one of these terms is called a head term, and we talked a little bit about this before when we talked about Bernoulli's equation. This is a pressure head, a velocity head, elevation head, head loss, shaft head. Okay. Like I said, we've talked about all this before with the regular Bernoulli's equation, but it looks a little different now. And that's because we've accounted for the possibility of losing some energy due to viscous effects, as well as bringing in energy or taking energy away through rotating shafts like a turbine or compressors, something like that. So let me talk a little bit about some of these terms here, or what this kind of looks like. So let me refer to the picture at the bottom. So let's say we have some pipe system that looks like this. Here's a lake, person in a sailboat on a lake, and we're going to pump some water out of that lake into a tank near our summer cottage here. Okay, so we have this pipe system with a pump in there. This is we're going to assume, steady flow in that pipe system. There's one inlet, one outlet. And what this extended Bernoulli's equation is, let me just write this down. Extended Bernoulli equation. I'm going to abbreviate it as EBE for short. It just is easier to refer to it that way. But we can apply that just like we did, the regular Bernoulli's equation for this kind of pipe system. What we can do is choose an inlet. I'll choose one right here. Now I'm going to talk about it in a moment. There's some streamline that goes from that point that'll eventually make its way through the pipe, through the pump, etc., and then come out right here. And let me call that point 2. I can apply this extended Bernoulli equation just like I did the regular Bernoulli equation between these points. From point 1 to point 2, I've just followed a streamline, or a stream tube. It has one inlet, one outlet. Again, there will be some streamline that goes from the free surface, eventually making its way into that pipe. As this lake gets completely discharged, eventually that point will make its way into the pipe. Okay, so I can apply this extended Bernoulli equation like I did Bernoulli's equation. I can look at the inlet, find out what the pressure is at point 1, what the velocity is at point 1, what the elevation is at point 1. I can do the same thing at the outlet, point 2 here. When I'm dealing with the inlet, in this particular case, the velocity at 1, the average velocity is basically 0. It's a large lake. Even though it is moving down, it's moving down so slowly that the velocity is almost 0. So I don't need to worry about the kinetic energy correction factor there. At the outlet, however, there is some velocity. So I would have to worry about the alpha here, the kinetic energy correction factor at the outlet. If it was laminar, I'd use a value of 2. If it was turbulent, I would use a value of 1. The way I can check whether it's laminar or turbulent is I just calculate the Reynolds number. If the Reynolds number is less than 2300, it'll be laminar. If it's more than 2300, it'll be turbulent. That number of 2300 comes from our Navier-Stokes equation analysis of Poiseuille flow or viscous laminar flow through a pipe. We'll come back to that in a different lecture as well. So this is the kind of like the energy coming in. This is the energy going out. But the energy coming in, some of it is lost due to viscous losses. We call that the head loss term. So as we go through this pipe, we have some viscous stresses that cause losses in the pipe. Some of that energy we put in to push the fluid through there is getting lost into heating up the fluid. So that's our head loss. So we're going to subtract some of that energy out. We put some energy in and we're going to have to subtract some of it out because of that viscous loss. And then we have the possibility of putting energy in or taking energy out. So for example, the pump here is an example of shaft work being done on the fluid. So if we have a pump, we would be adding energy in. We would have some shaft work being done on the fluid, and we express that as the shaft head term. Okay, and that, just to kind of relate that shaft head term to the power, here's the shaft head term, here's the power that the pump is putting into it, and you just divide it through by the mass flow rate and gravity, and that makes it the shaft head term. Okay, so if we have a pump, we can add in energy. So this is the energy we're starting with. We lose some energy due to viscous effects, but maybe we add some in because we have a pump doing work on our fluid. If we had a turbine, then this HS term would be negative because then we would be extracting some energy. And so we'd have the energy in, we lose some due to viscous effects, we're taking some out due to the turbine, and then this would be the energy we get out. By the way, I say energy, it's not, these terms do not have dimensions of energy. They actually all have dimensions of length. Like Z here is a length, so P over rho G is like a length. These terms actually are length. The term head quantities, I've mentioned this before with the regular Bernoulli's equation. It's just a historical nomenclature kind of term. They're just called head quantities. But these are all basically energy type terms. If you can see that more clearly if you go to this equation. This is why Fox and McDonald writes the energy equation like this, is because these all have energy per unit mass. You can see here, like, this is like a potential energy per unit mass, a kinetic energy per unit mass. This would be like the work due to pressure per unit mass, but it has the same units as energy. So really this expression here, the extended Bernoulli equation, is really just a statement of the first law of thermodynamics. That's how we derived it. So the extended Bernoulli equation really is just the first law applied to a pipe flow. For steady pipe flow with one inlet, one outlet, which basically means flowing along a streamline. And we can now account for velocity profiles through this kinetic energy correction factor. We can account for losses due to viscous effects, and we can incorporate rotating shafts in here as well, possibly through a pump, maybe through a turbine, something like that. Now the next couple of lectures, we're going to be focused on this head loss term. How do we actually calculate that for various scenarios? So we're going to look at that for just flow through a straight section of pipe. So we'll find the head loss due to that. And then you can find head losses due to flows through like pipe bends or T's or valves and things like that. Those kinds of losses, we often rely on experimental data. So we'll talk about that in upcoming lectures. But this equation here, the extended Bernoulli equation, we're going to be using all the time to analyze these kinds of pipe systems. We'll use it the same exact way that we use the regular Bernoulli equation to kind of connect two different points together. We have to evaluate what the pressure, velocity, and elevation are at the inlets and outlets. But now we need to also factor into the relation the kinetic energy correction factor. Is it laminar or turbulent? As well as figuring out what these head loss and shaft head terms are. So that's where we're headed in the next couple of lectures.